6 here. We have the function 2x cubed minus x, and they're saying do this sign, figure out what the signs of things would be at these different values of x for the original function, the derivative, and the second derivative. Okay? So, for the original function, first of all, if we plug in a -1, we'd have 2. We would have 2.
You might have to recalibrate.
Yeah, we have to recalibrate. I don't know what's going on with that. Here we go. All right. So we have 2 times -1 cubed minus a -1. Okay, that's a -1, so that's a -2 plus 1, which is negative. We didn't care about what the actual values were. We cared about what the sign was. Okay? So then, when we plug in 0, you plug in 0, you get 0. Okay? Now when you plug in 1, you get 2 minus 1, which is a positive 1. Okay? So,
Oh, I just need to plug in?
Yeah.
we just had to plug it in. So then we do the same thing for the first derivative. F of x is 6x squared minus 1. So if we plug in -1, we have 6 times -1 squared minus 1. So that's
Positive.
6 minus 1 is a positive 5. If we were to plug in 0 instead, we get a -1. And if we plug in a positive 1, we have 6 minus 1 is a positive 5 again. Okay? And then we do the same thing with our second derivative. So we're taking the derivative of the derivative, 12x. And you can see right here, without even plugging stuff in, okay, that we have
It's the same as this is the signs on the thing.
Yeah, if we plug in a -1, it's negative, 0, and positive. Okay?
It doesn't always work this way, right?
What do you mean?
Like it's not gonna look the same for each one, right?
No, it's not going to look the same for every function. Every function is going to be a little different. Now understand what these 3 things tell us. Okay? This is going to be important that you guys get into your heads here and see. What this right here tells us, and the f of x. Okay? If you were to look at this like a big number line, let me do it in black so it's, alright, we have -1, we have 0, and we have 1, okay? Now these are not critical values or anything like that, but we see 3 different things. First of all, at -1, we're below the x-axis. And we know that because f of x is negative. Alright? Looking at the derivative is positive, so we know that it's increasing. And then thirdly, because the second derivative is negative, we know that we are concave. What? No. Concave up or down?
Oh.
Concave down. Okay? Concave down.
Oh, okay.
Alright? That's, yeah, it's, if you think about it, we're still increasing, but it's slowing down. Like we would if we were coming towards the top of a hill. we're slowing down, so our acceleration is negative, but our function is technically still increasing. Okay? So, actually, technically, we're still getting faster, but we're getting faster at a slower rate. All right? Now, at 0, we have a 0 of the function. Okay, so that's an x-intercept. We are now decreasing. And then also, our second derivative equals 0. And as we're going to see today, that actually means that we have what's called a point of inflection. Point of inflection. And we'll define what that is in a moment. Okay? Scooch all this over.
Is that when like it changes?
That's where it changes concavity. That's right. It changes from being concave down to see here. Now it's concave up. All right, so we'll actually start from the bottom here. It's going to be concave up because the second derivative is positive. We're increasing again. And then also, we are above the x-axis. Okay? Okay? So, that's what we can tell from doing that sign analysis on the original function, the derivative, and the second derivative. Okay? Now, with number 1 here we aren't given a specific function, but we can tell a little bit about the function. Let's start, first of all, looking at the original function as we see it right here. Okay? A is above the x-axis, so we know the function is positive. At B, we know the function is negative. At C, we know it's positive. At D, we know it's positive. And at E, we know it's 0. Okay? So we're just looking at it. Where is it in relation to the x-axis? Okay? Now, so here, f of x, we're thinking position. Right?
Yeah.
For f prime of x, we're not thinking position anymore. We're thinking, is the function...
It's like velocity.
It's like velocity, right? Is it increasing or decreasing, right? Increasing or decreasing. So, at A, are we increasing or decreasing?
Decrease.
Decreasing, so f prime is
Negative.
negative. At B,
0.
it's 0. That's a min point, or at least appears to be, so we would say it's 0. At C, we're increasing again. At D, they told us it's 0. And then at E, we are decreasing, so again, it's negative. Okay? Now, our second derivative. For our second derivative, this one might be a little harder to see, but we're trying to think in terms of concavity. All right? So at A, what do you think our concavity would be at A?
Positive.
It's positive. As you're approaching a minimum point, and just after you get past a minimum point, you're going to be concave up. Now, let's look at B. At the minimum point, it's still going to be positive. We're concave up at a min point. Alright? At C, however, C, I know we're kind of guessing here, but C is going to be that point here where we're changing from being concave up to concave down. Here we were still speeding up in the positive direction. Now it starts to slow down in the positive direction. Okay? You still have the momentum to where you're speeding up after passing that min point, but then it starts to slow down as you approach the max point. Okay? So that C is that point of inflection. D, we would say we're concave downward, so the second derivative is negative. And at E, our second derivative is negative. Okay? So, there's our sign analysis for this. Notice, we didn't hit all of them here, but the original function had 1, 2, 3 zeros, right? When we had 3 zeros, how many critical values did we have?
3. No, wait.
Look at your second derivative, or your first derivative. How many critical points are there?
1.
2. And then how many points of inflection are there?
1.
1. Okay? Just like you lose a power on polynomials, unless you have like double roots or plateau points in there, typically you have so many zeros, then you'll have one less, and that'll be the number of critical values. Then you'll have one less than that, that'll tell you how many inflection points that you have. Okay? So that's, and again, unless you've got double roots in there or things like that, if it's a polynomial function, that's typically how it works out. Now, radical functions, all that other stuff, things get mixed up a little bit. But for regular polynomials, that's how it typically works. Okay? The turning points, we would also call those the extremes. Those are which 2 points? B and D. Okay? B and D. Now, question, how do I know that B is a min point? There's 2 ways I could prove it.
It goes from negative to positive.
Okay, good. At A, it's negative. The derivative is negative. At C, the derivative is positive. So since I have a sign change on either side of B, from negative to positive, I know we had a min point there at B. Okay? What's another way I could prove it?
By using the calculator?
No.
That's what I attempted on the quiz.
It is a critical value, right? And our second derivative is positive. Remember, we said there were 2 ways that you could show that something is a min point. You can either show a change of sign in your first derivative, or you can prove it's a critical value and that it's concave up at that point. Okay? If you have a critical value and it's concave up, it's a min point. If you have a critical value and the concavity is 0, that's a plateau point. Okay? If you have a critical value and it were negative, like at D, that proves that we have a max point. Okay? So if you studied calculus for a whole course or whatever, they'd call that the second derivative test. You have the first derivative test, which is, do we have a sign change, which we do, negative to positive. And then here we know this is a max because it changes from positive to negative. But the second derivative test is the one that says if we have a critical value and it's positive, we have a min point. If we have a critical value and second derivative is negative, we have a max point. Okay? So, alright, and then like we said, the point of inflection is C. Alright? And again, that's the point where we change from being concave up to concave down. Alright, does that make sense?
Yep.
Okay, so we got the general idea of concavity and what these inflection points or points of inflection are. What I want to look at today is just to kind of build on this idea, all right? And kind of take the two parts of your practice from Friday and put them together into what we're looking at today. We already mentioned and defined what a point of inflection was. The point of inflection is a point on a curve at which there's a change of curvature or concavity. All right? And a couple of things that you need to know. All right? The point of inflection occurs at x equals a if the second derivative at a equals 0. Okay? Also, you have to have a sign, the sign of f prime of x, f double prime of x changing at that point. So, it's got to be 0, and you've got to have a sign change in your second derivative. Okay, so you can see here, the sign diagram, we have a, and then it either changes from being concave up to being concave down, in which case you'd have something like this, and there's a right there, okay? Or, in this case, here's a, we're changing from concave down to concave up, so you might have something like this, and then it's, you know, there's a right there, okay? One way that I found kind of is helpful to explain what the point of inflection is I'm sure you've all probably seen a movie where, you know, the pilot gets knocked out in an airplane and all of a sudden the plane starts diving, right? And because he's out of control and it's going down and down and down. And what's gravity doing to that plane? It's pushing it and it's speeding up. It's going towards the ground faster and faster and faster. And then, miraculously, the pilot wakes up. And the point of inflection is like that moment when he wakes up and he grabs the stick and pulls back. Because the moment he pulls back, he's slowing down that downward acceleration. He's still going down for a while. But the moment he starts to pull up, it's slowing down that downward acceleration until finally he's not increasing his speed, but he's actually slowing down, and then eventually he's able to pull out of it. Okay, so that's kind of like this point right here. You know, he fell asleep at the wheel or got knocked out or whatever. He wakes up after a free fall, grabs the stick right there, and is pulling their way out of it. Okay? Kind of in reverse. I don't know how to explain the other one going upward, but you get the idea. Okay? I guess this is kind of like if you're shooting something up, this is the moment you let go and gravity starts to slow it down, you know? You're swinging something up. Oh, I know, like, you ever jump off a swing? You get swinging really high and you jump off? There we go. So here you're swinging, and the swing is still pushing you, but then you jump off, so it's not supporting you, and gravity starts to take over and slow you down, and then you land, hopefully, on your feet. So, here we go. That's just a little illustration, kind of to try to get the concept of what's happening with these points of inflection. So, let's take one example here all the way through. We're going to find the critical values and the intervals where we're increasing and decreasing. We're also going to find the points of inflection and the intervals of concavity. Okay? Now, one comment. I do have your quizzes to give back here a little bit later, but when you're asked for intervals, you need to actually give intervals, not just show a sign diagram and draw little arrows. Okay? So, for this example here, if we're going to do, first of all, increasing or decreasing, alright, we need our first derivative. F of x is 4x cubed minus 12x squared. Okay? And we need to set that equal to 0. So 4x cubed minus 12x squared equals 0. Because here we're finding our critical values. We'll just abbreviate that CVs. Critical values. Okay? And we solve this. How are we going to solve this?
You can pull out 4.
We can pull out a 4. What else can we?
X squared.
And an x squared. Good. So what's left?
X minus 3.
Good. X minus 3. So our critical values are where x equals 0 or 3. Okay?
And 3 is a double root.
Or 0 is a double root. That's right. Okay? So let's do a sign diagram real quickly here. We have 0 and we have 3. But say I try negative 1. Negative 1 squared is 1, so that's 4 times a negative 4, which is negative. So I know I'm negative to the left of 0. If I plug in a 1, I have 4 times 1 minus 3 is negative 2. So I know I'm negative between here as well. And then let's say I tried a 4. Okay, so I'm trying the right-hand side. That's going to be positive. 4 minus 3 is positive. So positive times a positive is positive. Okay? So, we could say that we are increasing over the interval from negative infinity up to 0.
No, we're decreasing.
Or, yeah, sorry, decreasing, thank you. Decreasing from negative infinity to 0, and then from 0 to 3. And we are increasing from 3 up to positive infinity. Okay? So those are the intervals where we are increasing or decreasing. Based on this, what could we say about 0 and 3?
Is a plateau point.
Okay? It appears as though 0 is a plateau point. 3 is going to be a minimum point. Because we were going down and now we're going up. Alright? We were decreasing, now we're increasing. Okay? So that's the first step. Now, to answer what this example is actually asking for, the intervals of concavity and points of reflection. What points of inflection do we have? Alright, so concavity. Well, our first derivative was 4x cubed minus 12x squared. So our second derivative is 12x squared minus 24x. So if I want a point of inflection, then I'm going to set this equal to 0. 0 equals 12x squared minus 24x. Okay?
12.
So good. Take a 12x out, and we get an x minus 2 left over. So our points of inflection occur where?
0 and 2.
0 and 2. Okay? 0 and 2. We said it's what it appears to be. Now, we do need to make sure that there is a change in concavity at those points. Alright? Now, since neither one is a double root, we're pretty sure that that's going to happen, but just to be safe, we do a sign diagram, and we have 0, and we have 2, and now we need to plug these in to our second derivative. Okay? So if I plug in a -1, that's going to be positive 12 minus a -24, so plus 24, so that's going to be positive. We're going to be concave up to the left of 0. Alright? Between 0 and 2, if I plug in a 1, 12 minus 24 is negative. So good, we do know that 0 is a point of inflection. Alright, because we have a change of sign. And then also, let's plug in a 3. That's going to be positive. And that's going to be negative, so we should get the value. So 12 times 9 is 108, minus 24 times 3 is 72. 108 minus 72 is going to be positive. Alright, so I know that 2 does give us a point of inflection as well, because we have a change of concavity. Alright? Now, we are concave up. We're concave up over the intervals from negative infinity up to 0.
And from 2 to positive infinity.
Yeah, or from 2 to positive infinity.
Do we include, like, is it included in both cases? Like, because the next one would be from 0 to 2. How are they both points of like going up and going down?
Well, here's kind of the thing. There's a distinction that you can make. It's kind of beyond the level that we have to be, where it's a matter of, is it like increasing or decreasing? Is it strictly decreasing or is it just decreasing?
Oh, okay.
So strictly decreasing means we would use a parenthesis. IB doesn't
Okay.
care if you put the parenthesis or the bracket there.
Okay.
If you were an AP Calc and we were doing this all year and going more in depth, then we would.
Okay.
Okay,
Makes sense.
so, alright, see ya.
Thank you. Bye.
Bye. So we have here the intervals of concavity, up and down. We have our points of inflection as well, okay? Or at least we have the values of x where we would have a point of inflection. We should go back, and the point of inflection would be the actual point on the graph. So 0, 5 is a point of inflection. And if I plug in a 2, I get 16 minus a 32 plus 5. So negative 16 plus 5 is negative 11. So 2, negative 11 would be our other point of inflection.
Wait, how did you find this again?
I just plugged it back in to the original function. Yeah, because we're trying to find a point on the graph.
Okay.
So that goes to the original function. Our plateau point would be at 0, 5. Okay. And our min point would be at 3. Let's see, that's going to be 81 minus 27 times 4. Well, that'd be a negative 27 plus 5, so negative 22. 3, negative 22. Okay.
Did you need to find the increasing and decreasing variables, or could you just go straight to finding concavity since it only asks you for?
Yeah, if you were doing this, they just asked for concavity. I just went through the whole thing to illustrate. Are you doing your quiz?
I have some questions if you have time. Like,
You have 5B.
no. What do Mr. Francis like to hear?
Alright, so, just to kind of wrap all this up. Right. Notice here, we have turning points, or we could call them critical points. We also have plateau points, and then we also have points of inflection. This is where the IB uses language that's a little bit different than what you might see in other calculus sources. Alright? But notice that plateau point that we found, it was a critical value, it came from a critical value, but it also came from a point of inflection, okay? And notice that happened at the point where we had a critical value that was a double root. That's a common occurrence there, all right? But this Venn diagram here, I think, is really, really helpful. It's from your textbook. And it also reminds us that these stationary points, or critical points, are points where f prime equals 0. The points of inflection you get when f double prime equals 0. All right. If I were just finding where f equals 0, what is that giving me?
Position.
Huh?
Position.
A position, and where would those be on our graph?
The 0, 6, and 1st.
The zeros, yeah. Don't forget about those. So that would be a good thing to just kind of keep in the back of your mind. When f is 0, I'm getting zeros or x-intercepts. When f prime is 0, I'm getting critical values, which will give me max or min points usually. When f double prime is 0, I'm getting points of inflection. Okay. So, all right. So that's just kind of what I wanted to wrap up here with concavity. The rest of our time, I wanted to give you a chance to practice with a little bit of this, okay? You've got A through H, and there's 5 parts for each one. You don't necessarily have to do all 5 parts, but definitely try, the first couple are really easy, so if you're still really fuzzy on the details of what we've been talking about, start with the easy ones, okay? D and E are some other polynomial ones, along with F and G, but then C and H, those ones involve some radicals, so they're a little bit different, okay? So take some time and work your way through those. And then number 10, Number 10, this is a great connection here. This was our probability density function for the normal distribution. Remember the normal PDF and you graph the bell curve? We can take the derivative of this.
That was awful.
It's an exponential, and you'll have to use the chain rule, right? But you can find the stationary point of the function, okay? Find where it's increasing and decreasing, and you can find points of inflection, okay? And then you can discuss, see what is this happening as x approaches positive and negative infinity, and sketch it and show the features, all right? So that one's kind of a good application, and also tying it to the stats we did in the past, okay?